So this is a new one in the mandatory pracs in the new senior secondary physics syllabus. It's not one that I think a lot of schools had done in the past. It's not super complicated, but it is a little bit challenging to get to work unless you have some really powerful magnets. Neodymium, different people pronounce it differently, but we have some very strong magnets. And what we're effectively doing is saying, okay, when you have a wire or any other conductor in a magnetic field and you pass a current through it, you end up having electrons traveling through. They have a velocity relative to the magnetic field, and so they experience a force. So the wire experiences a force in a direction perpendicular to the field. So we could talk about hand rules and so on, but we won't for the purposes of this. But what we've got here is quite a simple setup, really. We've got a 6-volt battery running to a thin copper wire. The copper wire is run between the two magnets, and in the circuit we've also got an ammeter to tell us when there's a current flowing, because basically the name of the experiment is force on a current carrying conductor. So we've got our conductor, we know when there's a current. So you can see that on the scale we've tared it to 0. So what's actually going to happen this time is, while the wire experiences a force, the magnets also experience a force. So Lenz's law tells us that when something exerts a force on one thing, it exerts a force back on the other. Indeed, Newton's third law tells us the same thing. So as the magnetic field exerts a force upward on the wire or downward, then the magnets themselves will be pushed in the opposite direction. So if I close the switch, you can see on the ammeter, we're on the 5 amp range of the ammeter. We've got about 3.5 amps. I'll measure that more precisely when I get round to the front of it. And on the balance, you can see, no you can't because my hand's in the way, you can see minus 0.1 grams. It's not a lot of force. It's expressed in terms of mass because that's what our balance does. So we'll have to convert that mass into a force, dividing by 9.8. But basically what happened was we went to an unmeasured negative mass. So that means that the magnets were experiencing a force upward, because a balance weighs a downward force as a mass and an upward force as a negative mass. So what we could actually do, let's do it. If we flip the terminals on the battery around, it's going to go negative on the ammeter, which won't be healthy for the ammeter. It'll be the same magnitude of charge. So I'm going to take the ammeter out of the circuit for this piece. I'll just take it out for its own protection. And then I will flip the terminals on the battery. And we should, if my physics is any good, see a positive mass, a positive force measured on the balance. So it's back at 0 with the switch closed. I'll try and pull the switch out of the way. And when I push it, we get a positive 0.07 gram force. It's interesting that the magnitude's different. I don't know whether there's some resistance in the ammeter that might account for that. Remember, the resistance of the wire is not particularly large, but you can see that the direction of that force has been reversed because we reversed the direction that the current was flowing in the wire. So hopefully that's relatively clear. We have a set of measurements, and again I will conduct a number of measurements and give you the data of different values of the current and different values of the force, and we can then calculate that the strength of the magnetic field, because we'll have F equals BIL. The force is the magnetic field strength times the current times the length of the conductor that's in the field. So we can actually calculate that. Okay, in this instance, although it's called the force on a current carrying conductor, what we actually calculated was the force on the magnets in relation to the current carrying conductor in a Newton's third law sort of way. So the magnetic field exerted a force on the wire, but then the wire exerted a force back on the magnetic field, which exerted a force on the magnets, effectively. So it's the change in the apparent mass of the magnets that we're actually measuring. So let's actually kind of set our situation up a little bit. We had two neodymium magnets. They were on metal holders, but we don't particularly care about that for our purposes right now. And this is a plan view down from the top. So we're looking down on top of the magnet. We've got a magnetic field of field strength B. So the field strength is indicated by how far apart the field lines are. And the field strength is what we're actually going to calculate in this case. So its strength is B, and that's a vector quantity. We've got a current flowing through a wire. The current is of magnitude I. Now, I is not a vector quantity, it's a scalar quantity, because although it's flowing in a particular direction, when you add currents at a junction in a circuit, it's just the algebraic sum, not the vector sum. So I is a scalar quantity, but the length of the wire that's within the field, because that's the length of the wire that we're interested about. So the length of the wire that's inside the magnetic field is L, and that is a vector. So it's a length of L meters. B is the magnetic field strength in Tesla. And we have this expression F equals B I L. So that's a vector, and of course a force is a vector. And it's BIL sine theta, where theta is the angle between the current carrying conductor and the field. But in this case, that's a right angle, and sine of 90 degrees is just 1. So in this case, we can, for practical purposes, ignore this because it just goes to 1. It's a multiplication by 1. But if the angles were not 90 degrees, if it was not mutually orthogonal between the two, then it would be a situation where we would have an angle coming in as well. That's just a scalar multiplication. It's just a number in this case. Now, unfortunately, on this kind of video, I can't show you hand gestures, but if you take your right hand, point your fingers in the direction of the field lines, many fingers, many field lines, point your thumb in the direction of the current as though you were hitchhiking, not that we encourage hitchhiking anymore, but your thumb is pointing down the page in the direction of the current. And if you're like me, your arm is quite twisted at the moment, then your palm is the direction of the push, the force that's acting. And in this case, that force will be acting upward out of the page. So I'm drawing an arrowhead shape. It looks a bit like this for upward out of the page. The convention we use is that downward into the page is like the tail of a receding arrow. That's the fletching, the feathers on the arrow going away from us, and this is the point of the arrow coming towards us. So in this case, the force that we're measuring is coming up, but of course the force on the magnets, which is the opposite force, will be going downward in this particular instance. So in our experiment, we might need a few pieces of data first, I think. So the mass of the whole arrangement of the forces and the currents, the mass of that is 184 gram equals 0.184 kilogram. We should work in SI units. So that's how heavy the thing was. So that means that the force acting on that is going to be given by F equals mg, or sorry, the force of gravity on that. And so we know its weight force in Newton is going to be that 0.184 times 9.8. So 0.184 times 9.8 is very close to the limitations we're doing, 1.8 Newton. That's the downward force due to gravity on the magnets, and that's going to change by a very small amount due to the force on the current carrying conductor. What else do we know? We measured our current, and for the first trial the current was minus 0.10 ampere. For the second trial, when we reversed the polarity, I think it was plus. No, sorry, I'm reading the wrong thing. Let me fix that. That was the force. Let's get rid of that. The current was 3.6 ampere. That was what was measured on the ammeter. And for the second piece, we didn't actually measure the current because we didn't want to drive the ammeter backward and damage it. So 3.6 amp was the current flowing. Now that's quite a big current. Currents in whole amperes, you certainly don't get in phones and other electronics and so on. You get them in household current and so on. But it's quite a solid current. It was a little thin wire, but it did carry that without burning out. So then the force that we got, and the force, remember, is a vector. I should be being consistent here. Mass is not itself a vector. G is a vector because it's an acceleration, so it has a direction. The force that was experienced was minus 0.10 Newton. No, it wasn't. It was minus 0.10 gram because the scale reads in gram. So we can turn that into newtons by multiplying it by 1.8. So, sorry, 9.8. 0.1 times 9.8 is just going to be 0.98. So 0.98 Newton is the force that was actually exerted. So, the distance that the wire travelled through the field, i.e. between the magnets, was a length vector of 0.02 meter. It was 2 centimeters, so 0.02 meters if we're using proper SI units. So now I think we have everything we need for our calculation, and I also think that calculation ended up being kind of pointless because we're interested in the difference in the force on the overall thing rather than in its absolute value, which is not that relevant. So we'll go with our F equals BIL. As I said, we can ignore the sine theta, and for the simplicity of writing, I'm going to ignore the vector signs as well. What we're trying to do is find B as the subject. So B equals F divided by IL. I just divided both sides by IL. So the force we know is minus 0.98 Newton. The current we know is 3.6. The length is 0.02. And I'm getting 13.6 Tesla. And again, that's quite a large magnetic field, but that's what we would expect because we had the powerful neodymium magnets. So I'm getting 13.6 Tesla as a result for that, for the strength of the magnetic field between the two magnets. So the force was simply, and I should carry through the minus sign. The minus sign is just about the direction of the actual force. And we did use we could actually have, no, let's actually do it a different way. We can make that a plus because the force upward on the magnets, because in other words, the balance thought that the mass had got less. So it gave us a negative mass because it thought that the mass had got less. But that was because the magnets were being forced upward by the force on the current carrying conductor, which means that the force acting on the wire was downward. And so this can also be a positive field, but that essentially just means the direction of the field in which way we were particularly setting up the situation. So our field in the situation above, our B, equals 13.6 Tesla, magnetic field strength. Thanks for that. There's obviously ways that we could make the apparatus fancier and more, or just fancier, more precise, more accurate, but hopefully you've got a good sense of what's actually going on with the physics of this situation, which is around about that issue of the fact that when you have current, when you have moving charge effectively, so you can either have a beam of individual electrons being fired through from an electron gun, and if so, each individual electron will experience a force, and that will be given by F equals Q, the charge, V, the velocity, which is a vector, and B, the field strength, which is also a vector, sine theta. So it's essentially the same thing, but it's for individual charges of charge Q. I is basically just a bunch of charge over a period of time passing through a conductor. And if we did a dimensional analysis, we would find out that because velocity is divided by time here and current is divided by time, or charge is divided by time to get current, these two are mathematically equivalent to each other if we did a dimensional analysis. But in this case, we had electrons flowing in the wire. We used the right-hand rule because we used conventional current. So conventional current flows from positive to negative. Electrons flow from negative to positive. I think I talked about this in the lecture videos. Right-hand rule for conventional current, left-hand rule for electron flow, but we should end up getting the same result either way. So because we would point our thumb in the opposite direction, our fingers would still go the same way, and if you do that with your left hand, you'll find that again the force is upward out of the page. Okay, I'll stop rabbiting on. I hope that's useful. See ya.